systems like industries where we have a lot of system, things which are where there are moving parts, and obviously we need to measure the 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 level of vibration that's there, because sometimes vibration could be undesirable, but there could be vibration which we need to monitor, or there could be some vibration limits that we want to put up or we want to control. So again, we need to have sensors which can measure this parameter called as acceleration, or in this case we have vibration also. We may do obviously some other use some other strategies which can give us this the measurement of the acceleration. Let's say we have discussed about position or velocity measurements, where we can let's say differentiate them to get the higher order terms like x double dot, which talks about the acceleration. But obviously if we talk about position, then we are double differentiating it, so the noise is amplified a lot. And if you're using velocity, again that signal is getting differentiated, and let's say the noise is getting amplified. So we do have systems or methods whereby we can directly measure the acceleration. So this thing, I think accelerometer was also there in your mechatronics course. We could not study that let's say in the form of the online lectures, but it was, I think, there in the course contents. But I thought, since I did not discuss that using the online lecture, so I should probably take up it in today's lecture. So it looks like something like this, so I'll just draw it here. This is a typical line diagram of an accelerometer. So this is in the purple color, I'm drawing the base of the moving object. So this represents the moving object here. Whose acceleration we need to measure, or we want to measure. And this block in this color, this represents the base or you can say base on frame. The frame of the accelerometer, it's resting on the moving object, and generally this is fixed with, let's say, could sometimes be fixed with nuts and bolts, so that there is no relative motion between the frame, or you can say base, and the moving object. So they are fixed let's say tightly, so that the motion of the object is exactly transferred to the frame of the accelerometer. So again, similar to the inertial navigation system, we have inertial concept here. Again, we make use of a mass. This is also referred to as seismic mass. Generally a very small, you can say a small amount of, let's say, object in the form of, let's say, is used in this accelerometer, so that's why we call it as seismic mass. And then it is let's say suspended like this. We have a spring and a damper that is connected to the frame, so obviously they are in parallel. Now this is the pointer from the mass on the base of the frame, and there is some graduations on the scale of the scale. All right, now we have, say, motion associated with the object which is moving actually. So let's assume that is x, which is, again, we can assume to be harmonic motion, so x naught cos of omega t, because we assume this is vibrating, it's some frequency, and it obviously has some amplitude x naught. And then because of this motion, this also base frame will also move of the accelerometer, but because the mass is not rigidly connected to the base, obviously mass will have a different, let's say, movement, or you can say motion. So let's take that as y. All right, and let's call another parameter as z, which defines as the relative motion between the mass and the object, which obviously would be y minus x. Fine. So now the mass is suspended like this. We have a spring whose, let's say, spring having some spring constant k, and you have a damper whose coefficient of damping is, let's say, c. All right. So it is also called as seismic instrument. Now, if we are basically using this concept in the measurement of acceleration. So if we try to analyze this, so what we are actually trying to do effectively is that the object which is moving or which is vibrating, we have an instrument connected to it, and then we have a mass suspended inside the instrument in such a way, or inside the frame in such a way, that it's connected with a certain amount of, let's say, a spring and a damper with a particular stiffness and damping coefficient. Now, obviously, the mass is also defined, the spring constant is also defined, and the damping is also defined. So the moment this object starts vibrating, this mass will also start moving. So we can get something called as the relative displacement using some other transducer. We call it as relative motion, or you can say a small transducer can be attached. I'll just maybe discuss it later on also in the same lecture. So that can give us the relative motion. So what does that motion correspond to? Actually, we'll see that by analyzing this system. So how we can use this system in the measurement of, you can say, acceleration and maybe the displacements also. So now if we analyze this as let's say, if we try to analyze this as a free body, in the form of free body diagram. So the mass m actually moves with, let's say, displacement y, and then because of the relative motion between the mass and the base, or you can say moving object, so we'll have this spring and the damping itself. Even by the motion of the mass, this will have some this will exert some restoring force, and also this will exert some damping force. So both these forces together actually will be acting on the mass, and the acceleration of the mass will be proportional to that. So by Newton's second law we can relate that thing. So if we assume that the mass is moving up in this way, so the force due to the spring actually will act in this form, k of y minus x, because it's not just the y, because there is also x, the motion, the object is moving and the mass is also moving. So obviously the relative motion, if the x and y is same, so then obviously there will be no spring force acting on the mass. But because there will be a relative motion the way we have designed this system, so we'll see that there will be an effect, or the net displacement of the spring, and accordingly there will be a spring force that will be exerted on this. And similarly we will have a damping force which will be proportional to the velocity. You can maybe write it here only. So we'll have c of y dot minus x dot. All right, so by Newton's second law, you can say, if we take all the, let's say, all the forces in the upward direction to be positive, then for example this is moving in this way, so obviously it will have an acceleration my double dot, because that's the absolute motion of the mass. So by Newton's second law we can say that the summation of the forces acting on this body is proportional to the acceleration. So the summation of forces is minus k of y minus x minus c of y dot minus x dot. So why this is minus or negative? Because we have assumed positive direction to be in the upward direction, and because the forces will always try to decelerate, or you can say it will try to pull it back or against the motion of the object. Similarly, what a damping does, it damps the motion, so obviously it's trying to decelerate, or you can say. So accordingly these forces will be the opposite direction. We have taken this as positive, so my double dot will be equal to the sum of the force, or summation of the forces, but forces are in the negative direction, so we write negative of k of y minus x and negative of c of y dot minus x dot. All right, so now this can be so we can look at this now in the form of a relative motion. So we have the let's say z as the parameter denoting the motion of the mass related to the frame. So z will be equal to y minus x. Alright, so we can write now this equation in the form of z also. So this will be like this: m z double dot plus c z dot plus k z is equal to minus of mx double dot. Alright, so y has been substituted as z plus x. So obviously this will be mz double dot plus mx double dot. So we can take these to the left, and the x double dot goes to the right as negative, and then from here we have y minus x as z. So this is kz, cz dot is all go positive to the left. So that's how we get this equation. So now we have got an equation in the form of z, which is the relative motion between the mass and the object which is moving, and this can be measured with some transducer. So obviously again we are using some indirect measurements here, because we don't just use this instrument or this mass, but we are using another transducer to measure that motion. So that's z, which we can actually measure. So we would like to get the output in that form. So z would be output for us, and x is actually the input, which is the motion of the object whose acceleration or displacement is to be measured. All right, so this is the equation, let's say, of the instrument that we have actually, let's say, designed for the measurement of acceleration. Now because we have assumed the harmonic this object to be moving, let's say, with some harmonic motion x naught cos of omega t with some frequency omega, so we can find out the x double dot also from here. So that will be x naught omega sine of omega t minus, then x double dot, if we differentiate it again, will be x naught omega square cos of omega t. Now if we substitute this expression back into this, so we'll get mz double dot plus cz dot plus kz is equal to, the minus and minus gets converted to plus, so we have m omega square x naught cos of omega t. All right, now if you remember, the this is nothing but a second order differential equation, okay, and you must have studied this in the vibrations also. Maybe this accelerometer was also taught in the vibrations. So we are getting a second order differential equation, a linear differential equation second order, with in the vibration it could be like with a forcing function m omega square x naught and cos of omega t. So this is the forcing function for us. So obviously in the solution of these differential equations we have seen something called as complementary functions and particular integrals. So with all those things we would solve this and we'll get the solution of the differential equation. But you must be remembering some expressions like this, where we would denote this by, let's say, something like z double dot plus 2 zeta omega n z dot plus omega n square z. So this is a very standard expression of second order systems, where we actually try to divide this by, let's say in this case, m. So k by m denotes omega n square, k by m. So if we divide this whole expression by m, then this becomes k by m, then we have omega n square. So that gives us the natural frequency of the system, which is actually given by k by m, which is a very standard expression. And similarly we have 2 zeta omega n is equal to c by m, and zeta is actually given by c by 2 omega n m, which can be substituted from here. We can have c by 2 under root of k, or you can say k by m, and outside we can have another m, similar what we are doing as a substitution. So obviously if this m goes inside, it's m square, so we have k by 2 root of km. So this is our damping ratio, and this is our natural frequency of the system, which is dependent on the physical parameters or physical let's say parts that we have designed the accelerometer for example the stiffness, the mass, the damping, on all those things. So as per our design of the accelerometer, we will have to obviously choose or finalize with c, k and m. Accordingly we'll have to define natural frequency of the system, and then the damping ratio of the system also. So now this goes back to the vibrations that you have already studied. Now we could relate now this with the let's say the amplitude which we call as Z naught, or we have something called as Z, which is the output is would be given by Z naught cos of omega t minus phi. So what this means is that the output will also be the output will also be following the input, but obviously it will be delayed by some it would have some phase shift, but it would be let's say harmonic again as per the input, which is the input we have taken to be x naught cos of omega t. So obviously the output will also follow the input, but obviously it will have a different amplitude and it will have a phase shift. So this is a very typical or standard thing that we have studied in the vibrations course. But the typical expression that we use for the ratio of output to the input is equal to something like this: r square by under root of 1 minus r square whole square plus 2 zeta r square, where r is nothing but the ratio of the frequency, you can say the forcing function, and the natural frequency of the system. This is also called as the frequency ratio. Now what does this tell us actually? It tells us if we plot now the graph between the r, which is the omega by omega, and the ratio of the frequencies with respect to, or you can say on the y-axis we have the z naught by x naught. So z naught by x naught in this case is nothing but displacement amplitude. So this is nothing but the ratio of the displacement amplitude. In this case we're not talking about acceleration, we'll just come to that from here only. So z naught by x naught here would simply refer to some amplitude ratio, isn't it? So z naught is also an amplitude, x naught is also an amplitude, or can of the signal, or of the forcing function, or you can say of the input, which is the motion of the object. So we'll have some amplitude. So we are defining nothing but the amplitude ratios of the output and the input, and we are trying to plot it with respect to the ratio of the frequency. So this is again a popular figure that you must have seen in the vibration. I'll just redraw it here. So this is how it looks like. Just mark 1 here. So same. The lowest one goes like this. Then the others go in between. All right, so this is near about 1. This is also 1, and can assume this to be 2, and this is, for example, 3. Similarly, we have say 2.0 as the ratio of the amplitudes. Now the each curve actually corresponds to different damping ratios. So if we have a damping ratio of 0.25, this is the response. If we have the damping ratio of 0.5, this is how it looks like. And the curve which is sorry, which is almost, I'll just draw another one that should look like more smoother, something like this. So let's talk about this one. So this is zeta 0.7, and this corresponds to zeta is equal to 1.0. So we call this as so we call this as the displacement response. So this is the displacement response of called as a seismic transducer. Okay, so this is nothing but the plot of z0 by x0 in terms of this r. So if you plot z0 by x0 with respect to r, this is what you would get for a particular value of zeta. So you fix zeta and then try to solve this and then try to plot this for different values of r. All right, so and change zeta and again plot it. So this is how it would look like. So what does this figure tell us is actually that if we see one z0 by x0 at 1, which is what we would like to have, that the output ratio output to input, let's say for example if it is equal to 1. So what does it tell us? That there is a curve, this one, which is fairly flat for a large values of r. All right, so but obviously it's before 1, let's say r less than 1, we don't see anything such like that, but after almost r is equal to 1, or you can say maybe r is equal to what they refer to as r is equal to under root 2. So at r is equal to under root 2, or r we can say greater than under root 2, which is somewhere around here 1.414, or maybe I have just drawn it, could be at the middle almost, as greater than root 2. So r greater than root 2, and for zeta is equal to 0.7. So what we are seeing is that the curves are flat. Okay, so this curve is not flat, this curve is not flat for that period, the others are also not flat. So if we choose zeta is equal to 0.7, if we design our accelerometer in such a way that our zeta is equal to 0.7, and we also choose our natural frequency, or sorry, the forcing frequency, which is more than root 2 of omega n, which means r is greater than root 2, so then we would obtain this type of response for this accelerometer. So omega obviously is under root of k by m, so choosing k and m in such a way, c is we have zeta is equal to c by 2 root km. So we try to tinker, or we try to play with these values of k, m and c in such a way that we get this type of response, which is almost flat from 1.414. So this thing is what is desired. So what would it mean is that if we try to if we're interested in displacement measurements at frequencies more than root 2 omega n, and if the damping ratio is around 0.7, so we can easily correspond to whatever has been measured by the displacement or you can say relative displacement transducer z0 is nothing but the displacement of the object whose is to be measured. तो z जो है हमारा यहाँ पर z बेसिकली हमारा एक ट्रांसड्यूसर यहाँ पर लगा होगा, चाहे वो पोटेंशियोमीटर होगा या एलवीडीटी लगा सकते हैं हम. तो जो z आएगा हमारा, उसका जो एम्पलीट्यूड होगा उस सिग्नल का, वो एम्पलीट्यूड कॉरेस्पॉन्ड करेगा हमारी जो ऑब्जेक्ट मूव करा उसके एम्पलीट्यूड को. सो इट्स काइंड ऑफ अ डिस्प्लेसमेंट मेजरमेंट इन दिस केस. So we would, and that would be possible only, that can be corresponded only if the ratio of the frequency is more than root 2, which means we can talk about measurement of displacement, or you can say displacement measurements for frequencies greater than root 2 omega n, यानी जो हमारी सिस्टम की नेचुरल फ्रीक्वेंसी है उससे 1.414 टाइम्स के आगे जितनी भी फ्रीक्वेंसीज है, मैंने कैसा भी ऑब्जेक्ट जो है वाइब्रेट कर रहा हो, उसकी हम डिस्प्लेसमेंट जो है इस तरीके से आराम से निकाल सकते हैं और उसको कॉरेस्पॉन्ड कर सकते हैं जो हमारा आउटपुट आएगा ट्रांसड्यूसर से. ठीक है, और अगर हमारे पास यही सिस्टम है, लेकिन इफ वी वांट टू एक्चुअली मेजर द लो फ्रीक्वेंसी डिस्प्लेसमेंट, अब हमारे पास लो फ्रीक्वेंसी डिस्प्लेसमेंट्स हैं, हमारे पास डिस्प्लेसमेंट मेजर करना है लेकिन लो फ्रीक्वेंसी है. ठीक है, देन इन दैट केस व्हाट वी वुड लाइक टू डू इज द ओमेगा एन ऑफ दैट. जैसे हमारे पास एक सिस्टम है, वो वाइब्रेट तो कर रहा है लेकिन उसकी जो फ्रीक्वेंसी ऑफ वाइब्रेशन है वो बहुत स्मॉल है. अब हमें उसकी डिस्प्लेसमेंट मेजर करनी है, तो हम यहाँ देख रहे हैं कि हमारा जो है सिस्टम ऐसा होना चाहिए कि तभी हम मेजर कर सकते हैं. देन फॉर दैट केस व्हाट वी वुड लाइक टू डू इज वी वुड लाइक टू रिड्यूस द ओमेगा. सो वी डिजाइन आवर accelerometer in such a way, or you can say the displacement transducer in such a way that we try to reduce omega n. जैसे हम omega n को reduce करेंगे तो r हमारा बढ़ जाएगा obviously, isn't it? So omega, because r is proportional to 1 by omega n. So as we reduce omega n, which actually would mean, so if we are reducing for, you can see we write it here like low frequency displacement measurements, low frequency displacement measurements, we use omega n, which should be small, so which means if it's proportional k by m, that means we have to either reduce k or increase mass. किन से मिलना आपको? आज नहीं आए, होपफुली कल आएंगे, नहीं आज नहीं आएंगे. So we, sorry, मोबाइल नंबर में ऐसे किसी का देता नहीं, मतलब विदाउट हिज परमिशन. सो आप कहाँ से आए? ठीक है, मैं उनको बोलता हूँ तो. So which means that we have to reduce the k, which means we can use a soft spring. ठीक है, or we have to increase the mass, but obviously we have to balance it with these things. बाबर सर्च ना सामत क्या innocent piking. ठीक है, so this device is useful for, let's say, displacement measurements of the vibrating instruments, obviously, but obviously with this constraint that the damping ratio has to be like this and the frequencies have to be very high, then only we'll have a flat curve, which would mean that the output of the transducer would be nothing but it would be z naught by x naught would be equal to 1. So 1 for zeta is equal to 0.7 and r greater than, sorry, root 2 omega n, so or r greater than root 2, so which means z naught will correspond to x naught. So whatever will be the input amplitude of the vibrating object, we can easily correspond it to the whatever output we are getting from the transducer, or the amplitude of that transducer signal, transduce an output. Fine. Now where does acceleration come in, or how do we look for the acceleration? So let's say using the equation that we have just now seen for the ratio of the amplitudes, z naught by x naught, which was equal to r square by under root of 1 minus r square whole square plus 2 zeta r whole square. So we can manipulate, or we can play with this equation again in such a way that if we again substitute r is equal to omega by omega n, if we substitute this back here and try to manipulate it in such a way that if we try to get it this way, omega n square z naught by omega square x naught. So this is nothing but just substituting r square, I think. So just r square is omega square by omega n square. Omega n square goes to the cross multiple, sorry, it goes to the numerator of the left hand side, and omega square goes to the denominator of the left hand side. So it's nothing but a very simple manipulation. So we'll get something like this. All right, and if we plot now this expression, or you can say omega n square z naught by omega square x naught. Now if you remember omega square x naught, which I am highlighting here, what is it? It is nothing but the amplitude of the input acceleration. So let me go back to the previous, let's say, part. So this is where we had defined the input somewhere here. Yes. So if this is the input acceleration that we had defined, position and then acceleration accordingly. So this part, or you can just neglect the negative sign here. So x naught omega square. So what does this define? This is nothing but if this is the acceleration, so this is the amplitude of the acceleration, or you can say the object's acceleration, the amplitude of the object's acceleration which is moving. So this is nothing but omega square x naught. So we are getting something like the amplitude, the ratio of the acceleration amplitudes. So now this would also refer to these two are nothing but the ratio of the amplitudes of the acceleration. So if we plot this graph now with these two in the let's say in the vertical axis, And again on the horizontal axis we have the ratio of the frequencies. So here we have omega n square z naught by, we can refer it by a naught also, which is nothing but the amplitude of the input acceleration. So we'll get something like this. So if this is the unity, this is 1, means corresponded same. So then this is something what it looks like. So we'll get something like this, where these curves correspond to zeta is equal to 0.25. This is, let's say, zeta is equal to 0.5. The flat one, this one corresponds to zeta is equal to 0.7. This is zeta is equal to 1.0. All right, and in the x-axis I'll just put it here. So let's say this is 1.0. This is this figure you may have not seen earlier. This is this x-axis has been plotted on the logarithmic scale. Otherwise it has a different look, similar to this one, but a little different look. So this is 0.4, this is 0.5, and then 6, 7, 8, 9, 10, 1, and then this is almost 10. So this is the logarithmic scale. So this corresponds to this figure. So we refer to this as the acceleration response of the seismic transducer. All right, let me just look at a different figure if it is available to us. Give me a moment. This is also fine. Z by y. Yeah, I think we can go ahead with the same one. So the only difference is that the scale at the bottom is logarithmic scale, and in the previous one that we had drawn, this was the normal scale, but in this one we have a logarithmic scale. We can draw a simple scale also, in which we will see something like a little shrunk kind of figure which is shrunk. But what is important in this case is that this ratio, which is omega n square z naught divided by a naught, which is nothing but the ratio of the acceleration amplitudes, is flat for zeta is equal to 0.7, this one, up to almost 1. Let's say the ratio equal to 1, or maybe if I have not drawn it properly, what we have from the text or what we have from the equations is that this will correspond to r less than 0.4 and zeta equal to 0.7. So which means that the relative motion of the mass with respect to the instrument frame, which is z in this case, would be the measure of the object's acceleration. So obviously this is the amplitude of that, and this is the amplitude of the input acceleration. So if it is equal to 1, which means whatever we are measuring as an output is nothing but the input. So that is, we can easily measure the amplitude of the acceleration with this type of system. But the main difference is that R has to be less than 4. In the previous one we had R is more than 1.414, which was root 2. So in this case, to measure the to use this seismic transducer that we have defined as a spring mass damper system, to use this as an accelerometer, we need to have R less than 0.4. So zeta is same for both, but this is the configuration for an accelerometer. So if we put this configuration, we have flat response. Whatever we are measuring, can multiply that with the natural frequency. The ratio of the two is equal to 1, so we can easily get actually the we can easily say measure the acceleration of the signal or acceleration of the object which is to be measured. So that can be easily corresponded to the transducer output. Whatever we are getting, the amplitude of the transducer, and whatever we are getting, we know the natural frequency of the system, we can easily find out the acceleration of the moving object in this case. Fine. So the main learning point from here is that if we have a seismic transducer, we can use it for both for example high frequency, let's say, accelerations, and we can also use it for generally in the earthquakes where the acceleration may not be too high but the displacement is generally quite good enough. In the high frequency accelerations, we generally would see, you must have seen a very high frequency vibrating objects, so they don't have a very high amplitude, they have very small amplitude. So as the frequencies increase, the amplitude generally goes down, or amplitude is attenuated. So for a low amplitude but for a very high acceleration, so you would need to measure the acceleration for as an accelerometer, so you need to design it this way. So the left part, so R less than 0.4, and if we want to use this typically as a displacement transducer in the case of an earthquake, so then using it this way on the right side would be preferable. So in that case, we would like to have R greater than root 2, which where R corresponds to the ratio of the frequencies. So which means omega by omega n. So frequency is more than root 2 of omega n. So omega n will be designed. So more than root 2 of omega n, we would use this as a seismic transducer. The output would be proportional to the displacement of the input. And if for frequencies very less, or R less than, for frequencies very high where R is less than 0.4, all right, so we can use this as an accelerometer where the output will be corresponds to the input acceleration amplitude directly. Fine. Any doubts in this? जी खबर वगैरह कोई आप में से कोई कुछ डाउट पूछना चाहेगा? जुबैर? आप लोगों ने थ्योरी ऑफ वाइब्रेशन किसने पढ़ा आपको? टॉम टू? नहीं, ऑनलाइन क्या ऑफलाइन ही? अच्छा, तो सर ने ये पढ़ा होगा? अच्छा, तो रिपीट हो गया मुझे लगता है पूरा। इसमें कुछ लग रहा है आपको मैंने कुछ गलत कहा या कुछ आपको डाउट लग रहा है? जी खबर, मुझे तो डाउट लग रहा है, आपको कह रहे हो? सर कह रहे पहले ही। हाँ, उसमें तो पूरा डेरिवेशन आएगा ना, टॉम में तो पूरा डेरिवेशन आएगा। नहीं, ये आपको समझ में आया कि ये एक्सेलरोमीटर कब यूज करते हैं और इसको एज ये कब यूज कर सकते हैं? सेस्मोमीटर वो आया समझ? तो ये इसकी कंस्ट्रक्शनल फीचर्स है। लेट्स से दिस इज हाउ दिस इज माउंटेड। ये आप सॉरी ये स्प्रिंग यहाँ लगाएं, दिस हैज टू बी पैरेलल। फर्स्ट थिंग इज दैट। सेकंड थिंग इज that this is generally जो हम Z मेजर करना था वो हम मेजर कर सकते हैं by some transducers. It could be any transducer that we are using, that's available to us, which can be easily mounted there. So this is referred to as the relative motion transducer. So this is how it is mounted. ठीक है, Second way is that, or you can easily say that there is again, I'll just maybe draw it roughly here. Maybe I can share a video also, give it little clear. उससे क्लियर थोड़ा सा होगा. तो ये हमारा अगर स्प्रिंग और डैम्पर इस तरह लगा है, तो इसको हम यहाँ पर सीधे जो है रेजिस्टेंस ट्रांसड्यूसर, और कैन से पोटेंशियोमीटर we can attach here, sorry, in the form of the variable resistor. We can measure the output voltage here between this point and this point. So this is the way this is connected. So this is the applied voltage, this is the resistor. As per the motion of the mass m, we can, this will change the resistance, and accordingly we have the potential between the two, which can be measured, which will be equal to the displacement, or can correspond to the displacement or acceleration of the object which is moving. Okay, so this is another way, and so we call this as the seismic transducer using resistance transducer. Then we can also make use of an arrangement like this. So this is called as seismic transducer using resistance strain gauges. इसमें क्या करते हैं बेसिकली, इसमें हम कैंटिलीवर एक लाते हैं, कैंटिलीवर स्प्रिंग जो हमें जो डैम्प सॉरी स्प्रिंग एक्शन चाहिए, तो हम can you don't just need a, or you don't, it's not necessary to have just a coiled spring. You can have springs in this form also. So we have a cantilever spring. Maybe damping is provided in a different form. In this case it could be a viscous liquid, that this is all suspended in a viscous liquid for which we know the damping coefficient, and for spring action we are attaching it with the cantilever spring. So as the body moves, this obviously mass will go up and down accordingly, and this spring this cantilever will deflect because of being compliant, and accordingly we have the strain gauges mounted here, whose resistance will change as per the deformation, and then using a Wheatstone bridge kind of an arrangement, we can basically measure the amount of displacement which we correspond to finally the displacement or the acceleration amplitude. Okay. And then we also have one more arrangement in which we directly mount a mass on the strips like this. So we put again strain gauges here. Okay. So let's say this is 2 strain gauges, 1, 2, 3, 4, 5, 6, 7, and 8. So the body will go up and down. So accordingly we have a little different kind of a Wheatstone bridge in which we have these two resistors together like this. This is the arrangement. अलीफ सर कॉल पे हैं. अब उसमें कुछ लोग नहीं जा सकते तब तक, यहाँ तो 10-12 ही लोग हैं, मैं दान ये बहन लोगों बेचारन. सेम लिंक तो वो क्या अभी मतलब he is kind of trying to enter the room, is it already in? अच्छा उनकी क्लास है कहाँ पे? अच्छा हनीफ सर की क्लास ऑलरेडी है. सो मैं क्या हनीफ सर को रिक्वेस्ट करूँ 5 मिनट और कि नहीं? जी सर 5 मिनट सर. हाँ चलिए बस 5 मिनट्स. हाँ 5 मिनट ठीक है. So in this one, the one that I've just drawn on the right side, let's say the longitudinal strain is actually induced in the strip. The strips. It's kind of a strip, a kind of a small column type of structures that you can assume small structures like this. So obviously, if the body or the mass moves, let's say in this case the m. So suppose this body moves up and down. So accordingly, there's a strain in this direction. So obviously, this is in the longitudinal direction, which is generally in the case the strips are generally stiff. So which means for us the spring constant will be very high. So omega n is equal to under root of k by m. So which means omega will be very high. Omega n is high. So if omega n is high, our r is less, isn't it? So r is less means on that scale which we have just drawn. So which means r less means 0.4 k less than that. So we can use this effectively as an accelerometer. ठीक है. So this is another configuration, and the last one is the piezoelectric, which is very popular. You do have something else also. I don't probably see that we covered everything because that will increase the quantum or the volume of the work here. But this is the last one, which is very popularly used. This is the piezoelectric one. So we call it as piezoelectric accelerometers. I think one of you had this thing as the topic for maybe the seminar or the discussions that we had, case studies. So in this case, we just use a crystal and we, let's say, load it with some mass again. Then we have something called as hemispherical spring, or we can have any other spring arrangement. So let's say here we mention the called as hemispherical spring. So what this spring does, so we have a crystal, it's a piezoelectric crystal here. So obviously this is the body which is moving. All right. So what happens is, because of the motion of this mass will also move. This is preloaded with a spring. So what happens as it moves, there's a relative motion between this mass and this moving object. So this piezoelectric crystal actually will get deformed, and obviously because of the deformations, we can there's a charge which is induced. We can measure that voltage, and that will correspond to the motion of the object, displacement or the acceleration. The only issue again with the piezoelectrics is that static, or we can say very low frequency, maybe measurements we may not be able to do with the piezoelectric ones. For example, in the seismic ones where we have low frequencies, तो उसमें इसमें इशू हो जाते हैं. पीजोइलेक्ट्रिक जनरली जो चार्ज होता है वो भी जैसे हमने कहा देखा है कि स्टैटिक जैसे हम पुश करेंगे उसको तो चार्ज एक निकलेगा, बट दैट विल लीक अवे, इट विल नॉट स्टे. So it has to be dynamic in nature, so that means moving. But generally piezoelectrics are preferred when we have high frequencies or high frequency measurements. So for low frequencies, there are some techniques where we use something called as a cathode follower that is used for the improving the response with the low frequency also. But this is the typical idea. In this case we use a piezoelectric actually this is a piezoelectric accelerometer. So in this case we don't use any external electricity or supply. जैसे हमने वहाँ पे देखा रजिस्टर या हमने जो अभी ब्रिज देखे, पीजोइलेक्ट्रिक में क्या है, चार्ज जो है खुद ब खुद डेवलप हो जाएगा बाय डिफॉर्मेशन, और इसके अंदर जो डिजाइन हम स्प्रिंग भी ऐसा करेंगे या मास भी ऐसा करेंगे कि वो डिफॉर्मेशन विल कॉरेस्पॉन्ड टू दी एक्सेलरेशन ऑफ द डिस्प्लेसमेंट ऑफ दिस ट्रांसफर. ठीक है, आई थिंक वी कैन स्टॉप हियर.